Newton's second law states that if a net force is applied to an object with a mass, that object will accelerate in the direction of the force. The acceleration is directly proportional to the magnitude of the net force and is inversely proportional to the mass of the object. It sounds like a lot of words just to say force is equal to ma. So let's unpack that a little bit and let's learn how to say that. I'm going to start by saying that when a force is applied to an object with mass, that object will accelerate. The acceleration is going to be directly proportional to the force. So directly proportional, the net force means that it's linked to the numerator, and inversely proportional to the mass of the object. So let's state that one more time. When an object has a force applied to it and the object has mass, the object will accelerate. That acceleration will be directly proportional to the force applied, or the net force, and inversely proportional to the mass of the object. We measure force in newtons, and a resultant force on a mass of 1 kilogram to give an acceleration of 1 meter per second would be 1 newton. Sometimes Newton's second law can be stated in terms of momentum. We haven't studied momentum yet. It's something that we do in matric. And then we'll draw these links. But I just want this to be in your notes now so that when you're studying at the end of matric, you can see the link as well. And basically it says the rate of change of momentum is directly proportional to the resultant force and is in the direction of the resultant force. So rate of change of momentum is mass times velocity, which you will learn, and rate of change is the change in time, which you will also learn. So don't panic about this slide. It's just there for at the end of matric when we've already done momentum, that you can see how it links. So let's do an example. This is a 2,000 kilogram car, and it moves from 20 meters per second to 30 meters per second in 5 seconds. Find the resultant force. Well, force is equal to mass times acceleration. Great, but they haven't given me acceleration. They've given me 2 velocities. They've given me a time. B bar, we should remember equations of motion. And we need to remember how to use all of our equations of motion. So let's go through this quickly. In this case, I've got a final velocity, I've got an initial velocity, I've got a time, and I'm interested in an acceleration. So V is equal to U plus AT. So final velocity is 30, initial velocity 20, and time is 5. When I rearrange that, I get an acceleration of 2 meters per second squared, or 2 meters per second. I now take that acceleration, force, mass is 2,000 kilograms, multiply that by 2 meters per second squared, and I land up with 4,000 newtons that the car's engine is applying as a resultant force causing this vehicle to go forwards. The driver of a car sees an obstruction ahead and applies brakes. The car hits the obstruction at a velocity of 7 meters per second and comes to rest after traveling a distance of 5 meters. If the driver has a mass of 80 kilograms and is wearing his safety belt, calculate the time it takes for that car to come to rest. So, time it takes, we're going to need an equation of motion. So if I'm going to work out the time taken for the car to come to rest, I'm going to need an equation of motion. I know the distance and I know a final and initial velocity. So it's S is V plus U over 2 times some or other time when we've got acceleration. Substituting in the values, 5 is equal to 7. It is 0 plus 7, it doesn't matter, 7 plus 0, divided by 2 time. And when I rearrange that, I find the time it takes for the object to come to rest is 1,43 seconds. The next thing they ask is what is the average force exerted by the belt on the driver during the collision. So remember that the force of the driver on the belt, because the driver is going to be flung forward due to inertia, and then the belt will exert an equal but opposite force, and that force is going to be equal to mass times acceleration. I know the mass of this driver, he's 80 kilograms, or she's 80 kilograms, and we're looking for an acceleration. So we're going to have to use an equation of motion. V squared equals u squared plus 2as. I don't want to carry my mistake, a potential mistake, from the time over there. And so I'm going to say I ended at 0, 7 squared, which is 49, plus 2, I don't know my acceleration, I do know my distance is 5. When I rearrange that, I find I get negative 4,9 meters per second squared. So in other words, it slowed down at that rate. I put that in. So the car is going to, the man is going to exert a force forwards on the seat belt of 392 newtons, and this is going to be exerted back onto the man. Whenever you've got a Newton 2 problem, the first thing you need to always consider is that you have to consider what forces are acting on the object. You'll need to find the resultant force and see if there are any opposing forces like friction or anything like that. Draw and label a force diagram, or another thing that we can do is draw and label a free body diagram. Then we're going to apply F equals ma and create links. Now, let me show you what I mean by that. If I have an example such as this, I've got all surfaces and pulleys in this diagram are frictionless, so that's great. So let's just consider the two blocks. The first block is a 4 kilogram block. Quite obviously, it will have a weight acting downwards. It will have a normal acting upwards. There is no friction. The tension is acting towards the right, nothing holding it back. Then it's asking for us to do the 3 kilogram block. Not sure why that says 22, let's go with 3. The 3 kilogram block obviously has weight acting down and it has tension acting up. What's really important to understand at this point is that the tension in this rope, T1 and T2, have to be equal to each other. You can't have part of a rope tight and another part slack. I mean, take a rope and try and make half of it tight and half of it slack. If it's got tension in, it's going to have exactly the same tension all the way through. So really important, T1 is equal to T2. That's the link that I'm talking about. Obviously, these two forces are in equilibrium, so we don't need to consider that. We then have to consider that the weight is going to be equal to 3 times 9,8, and we get 29,4 newtons downwards. And then that whole thing is, they want to know what is the acceleration of this block. So we need to know the net force on this block. So let's go back to the original block. The net force, there's only one force, tension. So the force resultant is the tension, which must be equal to the mass times the acceleration of that block. The mass of that block is 4 kilograms. I don't know its acceleration. And the tension is T1. We do know, looking at the second block, that the force resultant must be equal to, and let's think about this now. Obviously, this block is going to go downwards. That's the nature of things. Gravitational acceleration is going to pull that down. There's no friction holding it back, so this 4 kilogram block can't be heavy enough to hold it from going down. It's going to go down, which means that weight has to be bigger than tension in this particular story. So it is going to be, the resultant force is going to be the big force of weight down minus the small force of tension. But I know what tension is. The tension is the same for both of these, so I can substitute that value in. And I'm going to say the mass of the 3 kilogram block is 3. The acceleration is the same for the whole system, 29,4 plus 4a. So that's a negative sign. So bring that over to the other side. I'll end up with 7a is equal to 29,4. Divide both sides by 7. and my acceleration turns out to be 4,2 meters per second squared. And it says calculate the acceleration. Remember, acceleration is a vector quantity, so if I'm considering the acceleration of the 3 kilogram block, it must be coming downwards.